So if anyone has any questions or comments or anything during the talk, just raise your hand, shout out a question, whatever, and I'll try to take it there, or I will ask to give the answer later. So I like to be happy, but most of the time recently, or the last, let's say 3 months, I've been quite bitter. And that bitterness has kind of, I think, affected this talk a bit. So why am I bitter? That's because basically nothing works, right? We have an infrastructure and a stack that I phrased at very late night on Twitter once is basically shit all the way down, right? And if you read my tweets, don't read the ones at Friday night because they tend to be many and upsetting. So as we built Fastly, we discovered these issues everywhere. And you Google them, and you get no result except one guy that 4 years ago asked the same question. No one answered, and 2 weeks later he replied, oh, I figured it out, and that's all. And that's like the only thing you see on the internet. And you're like, why am I here again? Like, why is no one else doing this? And sometimes you then you read the actual source code, and you're like, what on earth were they thinking? Like, who would do such a thing? And so I'll start off with a deep dive. It's pretty technical in Fastly land. And you see this graph. Ignore the cutouts. That's because Ganglia, that specific Ganglia server that I pulled this from was down during those times. But it's not a very happy server, right? Specifically, those spikes. They do not look like happy spikes, and they're coming very rapidly. There we have another one. And you're like, OK, so why? So you go look at the next graph. This is not a happy memory graph either, specifically that. You're like, what the hell happened here? Why did it suddenly evict on the order of 10 gigs from the page cache for no apparent reason? The other ones are me restarting the daemon, so ignore those. And then you read this. I'm also very happy with just what it does to interactive performance. Admittedly, my test case is really trivial. Reading email in a web browser, scrolling around a bit while doing a make-j64 on the kernel at the same time. But it's a test case that is very relevant for me, and it's a huge improvement. So we all, who runs Linux servers here? You all, we all run servers whose primary developers benchmark is if he can compile the kernel and surf the web at the same time. Right? Like, and that's where we are now. 10 years ago, we rebooted Windows machines every now and then to keep them running. Now we reboot Linux machines every now and then to keep them running, because otherwise they die. And God knows if anyone cares that actually develops Linux. No, because they all develop it for the desktop. And then I hear Ubuntu talking yesterday about some new fancy orchestration. All I can think of, make the damn ground-based operating system work. Like, don't ship Upstart with a long-term release that doesn't support, et cetera, in the restart. Like, why would you do that? Why would you hate server people that much? Why would you enable, like, the apt-get install recommended by default? And suddenly, like, I do apt-get install screen, and I end up with X Windows, Apache, and jQuery, because there is a screen jQuery Ajax UI that it installs by recommended, right? So this is part of what we're dealing with. Like, no one is really caring from our side, seemingly, about what's important to us. Yeah. So then there's NUMA. And I don't know, Mandy, if you're in here, but whoever did the NUMA support in Linux, yeah, go fuck yourself. So there's this syscontrol zone reclaim mode. Who knows what it does? You've been bitten by it? Have you been bitten by it?
Oh, yeah. I actually brought it.
Say what? OK. So there's a little gem. Tells the kernel whether it should swap or use memory from the correct NUMA node. I mean, putting it out there. The latency for a NUMA miss is, I don't know, a couple of extra 100 nanoseconds at most. The latency for a swap read is 200 microseconds on an SSD. When would it ever be a good idea to swap instead of pulling the wrong NUMA node? I would like someone to answer me that. And this used not to be the default, and then the latest Xeons switched the weighting of how expensive NUMA was, and yeah, suddenly you started having eviction problems. So that explains that. There's one NUMA node free, and the kernel decides that it doesn't want to use it. So we start varnish with NUMA control, interleave, and we set the reclaim mode to 0, and we set the zone mode to zone or whatever, and that usually fixes it. It doesn't always fix it. Sometimes it gets confused. Sometimes it still doesn't do what you want, but it mostly fixes it. Now, I actually made a huge error earlier when I said, let's go into NUMA, and I just went down there, because it looked like the obvious thing. And this is something I see people do a lot. They don't actually look at the data, me included. If you actually look at the data, the load spike and the memory drop is not actually related directly. In fact, the second one doesn't have any memory pressure indication at all. The third one is after a restart or after a manual eviction. So, time to dig deeper. Why is this happening? So every time someone says correlation is not causation to me, I pretty much want to punch them these days. Like, I know this, but I also know that there's generally some truth in that direction. And yeah. So what do? We have ganglia. We have a lot of charge. 396 per machine. There are about another 200-300 metrics I still want to monitor, but I've been told I need to pay a ton of money for a new metric server because we're overloading RRD by having all of these metrics. So with 396 charge, I should be able to see some freaking correlation, right? No, not a single one of them. Every single one of them has weirdness on it. Nothing correlates to the load spikes. So then, the only thing to do at, peak time or whatever, usually 11 p.m. on Friday, is log into the server and sit there and wait until the load spike happens, and with my eyes see what the hell the machine is doing. And to that, you use latency top. Who uses latency top? Okay. Everyone else, use it. It's actually really fantastic. If you want to be a bit more hardcore, you can use power top. It was originally developed for laptops, and Android people use it. But it actually tells you what the machine is waking up for all the time, which is pretty useful. So latency top will tell you what a machine actually is blocking on. And in this case, it's blocking on sleep on page. This is another kernel gem. This is actually, I didn't have one. I couldn't find a latency top from when the machine was acting really badly. So this is one where I kind of faked the memory pressure by typing sync many times. Usually that number, you'll see that number be like 600-700 milliseconds. And the page fault will still be like 18 milliseconds. Like, why is it sleeping on page or there's no page fault happening? And it's a request that shouldn't even touch disk. So what is load? It's the most misunderstood measurement, I think. A high load is not actually bad. A low load is not necessarily good or bad. Load is just a process cannot execute because it's waiting for something. So if you want to create a high load, fire up an NFS server, fire up a client, open 1,000 file handles, 1,000 processes that all read 1 byte at a time, kill the NFS server, and you have a load of 1,000. The machine is still idle and can do whatever it wants. You still have a load of 1,000. So generally, people think of that as I/O or CPU. It's also waiting for the kernel. And you think of the kernel as this magic entity that will always deliver results quickly, fast, instantly. Yeah, not so much. So look at this. Anyone know what output this comes from? Good. Look at that. It's scanning 1 million pages a second to evict 7,000 pages. Then it scans 900,000 pages to evict 48,000 pages. While it does this, it has 20% memory free. Why is it doing this? I can only assume that there is a very, very good reason that someone that is way more intelligent than me has figured out that this is the right way to do it, or the kernel is written by desktop developers. I think it's later. So you're like, OK, now we kind of figured something out. And this happens exactly when the load spike happens. So now I have some form of correlation. Something that, with many, many hours of digging, and I saw it, I was there, it happened, I know they were related, and our latency on our requests spiked a bit. So there's this thing called congested mode, where the kernel will pause processes for 100 milliseconds when it can't satisfy their page demand. 100 milliseconds is a very long period of time. It's kind of forever compared to how fast your machine really is. And it does this when it tries to reach back to the high watermark. So Linux has a low and a high watermark. And when it reaches the low one, it goes, hey, I need to reach the high one, and bam, tries to free as much memory as possible until it reaches the high one. So we tried tuning it. We set the min-free kilobytes to high, going, well, then there will never be memory pressure because it will try lazily to always keep 2 gigs free. Yeah, no. So the watermarks are ratios of min-free kilobytes. So the higher the min-free kilobyte is, the larger the distance between the small watermark and the high watermark is. And when it reaches that low one, oh, fuck, it's just going to try and evict all those pages as fast as possible. So at 200K, it will purge 40K in one go. At 1.5 gig, it will purge half a gig. And while it's evicting that half a gig, it's congesting your threads or your apps and telling them to go hold off and sleep, even though there is 1.5 gig of RAM free. I guess that's the right thing to do. So the quick solution is change low min-free kilobytes. If you do that, you running out of DMA space. And if you do a lot of network traffic, the DMA space is actually important because that's where the network card does zero copy stuff from to avoid having to copy memory in and out on the DMA. So basically, you have a DMA 32 zone, which is a wonderful relic of a very, very distant past. And then you have a low zone, and then you have the high NUMA zones. And so what the reserve ratio does is make sure that you protect that low zone, the DMA and the DMA 32. Because if you don't, you will have load spikes more at order of 10,000 when the kernel runs out of space to put packets or high order allocations. And then it needs to do compaction, and that's its own whole mess. However, a lot of people I work with would say, yeah, well, done, let's go home. This still sucks. We don't know what's going on, so we can't actually fix it. We applied a patch. And this is one of the talks yesterday was stop firefighting. I think one of the reasons we firefight so much is because we don't really understand what we did to fix something. And if you don't fix it, it ain't actually fixed. Right? Bugs don't magically go away. There isn't any magic tuning thing you can do that will make everything work better. I wish there was, but there really isn't. It would be easier if they were documented, though. But, so we need to understand what is actually going on here. So now I'm trying to run a website or a web service. I'm trying to make it fast. And I'm down in the page cache code. This seems very wrong to me. Why am I here? Right? But it's shit all the way down. I haven't had to go into network drivers yet, but after the last kernel panic, I probably will have to. So the page cache is this wonderful thing that, again, is pretty misunderstood. People think that the memory is free. It isn't. People think that the memory is used. It isn't. It's kind of in the middle. It's also a mix of an LRU and a FIFO. So the active memory is kept on LRU. I could actually be misunderstanding this, but this is my understanding after reading enough LKML and kernel code. When you reach the end of the LRU, you get put on the FIFO. The FIFO contains all inactive memory, which is very cheap to account for because when you access it, the hardware will flip the reference bit. And when it gets to the end of the FIFO, if that bit is set, it gets put to the beginning of the FIFO, to the LRU. We have 85 gigs of page cache. That's a lot of pages. A lot of them. So even if we evict a couple of thousand a second, you will spend a couple of hours going through that FIFO. So nearly every single page that comes off the FIFO has been referenced. Hence, we get this. And what does it need to do? Well, it needs to put them back on the LRU and grab the next one. So it has a 7.7% chance of being able to evict. Okay. So we can fix this. So there is a set of old school, apparently, POSIX commands that lets you tell the kernel how you want to use memory. Half of them are actually ignored by the kernel, and half of them do things. The one that we ended up using is MADV sequential. It actually does something. It does two things. It should really be used by more things, but apparently no one knows about it, and it is pretty much undocumented, except in certain POSIX books and the 5-line man page. And LKML disagrees with itself each year what the flags actually do. What it does do is it turns on massive read ahead. And when I say massive, it's like a factor of 10. I think the min read size becomes like 1.2 megs. And then it just uses the FIFO. It goes like, you're probably not going to see these again. They're just going to churn through, and then we're going to get rid of them. 99.99% VM efficiency on eviction. Things work much, much better, except our disks are kind of doing a lot of work. They're now reading 50 megs per second to deliver 5 megabytes per second of network traffic or something like that. Oh, okay. They're SSDs, so they're fine, but whatever. Should probably fix that. There's the magic sys directory in Linux. How many of you have dwelled into it? There is like a lot of it there, and there is nothing documented about it. I believe there might actually be a magic fix everything that's wrong about me thing in there, but no one will ever find it. So on the schedule, you have read-ahead kilobytes. So you can echo 0 into it, and now the read-ahead setting for that drive is 0, except it isn't. It is only 0. It's what it initializes the application with. So you need to do it before you start your application, and you can't change it for that specific application thereafter. But any new application will use that as its baseline for how it should adapt read-ahead based on the hit ratio. So we turned off read-ahead, and that kind of solved it. Except that's still a hacky solution. We're now FIFOing 86 gigabytes of cache. That's not really that good. Like, we should be able to do better. We should be able to be more efficient on what we actually do with the pages. And since the kernel can't do it, we need to do it ourselves. But we have our own LRU, and we can tell the kernel using Madvise and Fadvise, get rid of these pages. And it works. And incidentally, how many of you have ever slowed a machine down by doing grep on a 5 gig file by mistake. Yeah. If grep just used Madvise don't need, that wouldn't happen. If rsync just used it, it wouldn't happen. Apparently, our tools are written in the, 1980s, and they're still there. There's no reason why any of our one-shot tools should actually be consuming buffer space and then evicting and then causing swapping if you run with swap on, which I recommend you don't. So, yeah. This is the code that fixes it. So, turns out that you need to msync before, because otherwise you'll just nuke the pages, except you probably won't because of how I read the kernel, but that's what it says. And then you need to madvise and fadvise because it's both a file handle and a memory map. Once you do this, the kernel will actually get rid of those pages and put them back on the free list and reuse. So you can now tell the kernel exactly what to do. And that bounded our latency very well and decreased our long-term I/O read quite a lot. So is the conclusion that Linux is broken and undocumented? Yeah, kind of. The real conclusion is, if you don't understand your system, you shouldn't be running it. If you don't know how to dig deep into any level of the stack, then go hire someone that does it or outsource it. Right? It's your system. You need to be able to do this. And thankfully, we're running open source. So we can actually look at the source code. We don't have to go to a vendor and beat them up too much. Though sometimes I wish there was a vendor I could beat up. But it really is your responsibility. And if you care about performance, and if you care about efficiency, you need to be able to look at it and go there's something wrong here, and not settle for the first answer or the second, but actually find out what is going wrong inside the machine, and then fix it. And if we couldn't fix it by using Madvise, we would have patched the kernel, right? And don't be afraid of doing that. Don't be afraid of fixing it where it belongs. A lot of operational complexity comes from the fact that we tried to fix it at the wrong abstraction level, right? This is a good one. Why do we have large layer 2 networks in data centers? We do it because people foolishly want vMotion. Why do they want vMotion? Because their apps can't survive moving machines without it. And now we have very, very expensive, complex layer 2 switch networks in our data centers that don't scale, right? So network engineers have to solve a problem caused by bad application development by very, very expensive hardware that's very, very easy to fail. And the same applies the other way. Why the application needs something from the kernel. If the kernel doesn't provide it, it's open source. Just add it and write your own method. We did another wonderful thing. We compiled out fsync of our kernel. It does wonders for your performance. Don't do it if you actually run a database. So why do we care? So Fastly has cache servers around the world, and our goal is to return that content in less than 1 millisecond on the 95th percentile. You hit that page congestion window, and that's a 100 millisecond delay from the kernel. We shot our target of 1 millisecond pretty badly there, and the machine is kind of even not busy. So we need to care. We need to get around and fix that problem and make sure that we never run into congested memory. So I had a nice conversation a little while ago with this guy. It did involve SSDs, but they're tangential to the story. And he goes, well, I'm reaching a point where I need to shard. And I go why do you need to shard? And he's to make it scale. I'm well, what do you mean? He's well, it doesn't perform. Why doesn't it perform? Because it isn't sharded. And you're whoa. No, but why doesn't it perform? Oh, we use joins. Why are joins bad? Oh, because you can't shard them. It's for fuck's sake, have you no idea what you're doing? And so this continued for a while, and that was his resolution. He needed to shard so he could make it fast, and to shard he needed to get away from the joins, and the joins prevented him from sharding, which is why he wasn't fast. And that's what happens, when you don't understand why things are slow. Joins are slow because they don't have disk locality and because they fuck the CPU up a bit. SSDs kind of help that. Actually, they help that a lot. But I worked at LiveJournal. We sharded. We didn't do it because it was fun. We didn't do it because we enjoyed it. We did it because there was nothing else that could handle our write load. I'm pretty sure that if we didn't have to shard, we wouldn't have. Right? It's not like Brad woke up and said, I need to shard because I need to. It was, I need to shard because we're out of write capacity on our database masters. And those databases were freaking slow, and those machines were freaking slow. We had to shard. We had no other option. Now, if you're still on EC2, that means you're still stuck in the last decade on hardware, so you still have to shard. I feel sorry for you. Actually, I don't. I don't. You're paying the same for hardware as you did in 2008. How does that feel? Because I'm pretty sure that my laptop can run about, I don't know, 50 M1 smalls faster than Amazon can. So scaling out, is all good and so. But in the same way, mythical man month also applies to serving pages. Netflix is still fucking slow, no matter how many EC2 instances they use. Yeah, I mean, slide kind of sums it up. Throw slow shit after slow shit, and you end up with a lot of parallel slow shit. So we scale out too. I mean, you have to, right? But we have wonderful hardware these days. The machines are really, really fast. They can do wonderful things, and we're not using them. We're wasting them. We're buying machines and running like a request a second per CPU. Like, what's up with that? I had an opportunity and fortunate opportunity to play with a pretty fantastic machine a little while ago. It was a 80-core Intel machine. It had a terabyte of RAM. It only had 2 SSDs in it, but you could fit in 48. And it had 8 CPUs with 10 cores at 2.4 gigahertz each with 36 meg of level 2 cache. That was a pretty eye-opening experience, if nothing else because ATOP crashed because I don't have enough buffer space to show all the CPUs. There's 160 of them. So, I was like, how would Linus fill up this machine? So I did a make-J 160 on it. Timed it. I should have, but if I installed any mail reader on that machine, it would have crashed. So the user time reported by time when that compiled was 190 minutes, and the real time was 3 minutes. It had 8 10 gig E cards, and was about 24,000 times faster than an M1 Micro. It's 24,000 times faster. Or 1,200 times faster than an M1 Micro that's bursting. Or 1,600 times faster than M1 Small. Right? And I look at that hardware and it's like, it's kind of over the top. But then I look at my laptop and go, I bought that laptop a couple of months ago. It has 4 cores, looks like 8 with hyperthreading, 16 gig of RAM and an SSD in it. It is more powerful than a server I bought 2 years ago. So I'm looking at that 80-core machine and going like, holy crap, that's us in a couple of years. Like all of our deployments. And nothing we have scales on it. Like we got memcache to 1.5 million requests per second. Like 1.5 million requests per second sounds pretty impressive. Until we realize we get 700,000 per second on a 12-core machine. Right? And so while scaling out is good, we also need to know how to scale up. Because we need to be able to use the performance we have. And to achieve good latency, you need that. People talk about the low power ARM blah shit. Who here wants lots of small, slow CPUs, really slow CPUs? See, there's no great market demand. I'm pretty sure most of you like it, I want lots of fast CPUs. Lots of them, as many as possible. And that's, I think, where we're going. Like this 10-core machine, this machine is pretty beastie, but it's only using 12 watts per core, and those cores are pretty impressive. And the problem with the ARM stuff, I'm off on a tangent, but I'll continue. The problem is that we have not solved the network problem. Networks are still very, very slow compared to anything else, which is why scaling out is problematic. There's a paper just out about low latency networking. Go read it, it's good. Inside that 80-core machine, I have a faster network than you can ever build outside it, right? And that's important. Even if I run 8 processes, each in its own NUMA node, I have a network that supports low latency over a bus instead of over a slow network. And I believe that scaling up is going to become more and more important to actually efficiently use the hardware that we have. And scaling out is still going to be important and still necessary, but it wastes a ton of money today in the way we do it. So by scaling up, we can do this. That's our time to first byte over the last 60 seconds on one of the machines. I took it about an hour ago, or in milliseconds. Right? So sleeping 100 milliseconds is pretty disturbing. Even like the fact that context switches, the maximum latency on the scheduler is 3 milliseconds is pretty disturbing. But this is what you can do when you optimize hardware and software together, kernel and your own software and the hardware. And you look at it and you measure every step and you go, like, where can I make it faster? You can gain a lot of advantage. And if you virtualize and you control the underlying hardware, you can still do it. If you virtualize on shitty hardware someone else runs with a bad network, then you can't do it. So go back to why again. So I joined Wikia in 2007. I don't know, is anyone not familiar with Wikia by now? You're all gamers. When I joined Wikia to when I left in June, we grew our bandwidth between 5 and 6x year on year. And we went from 0 revenue to apparently profitable, I've been told, and from a couple of million users to now 58 million users. And what amazes me about the bandwidth numbers for that is actually it's all text content. It's not video. It's an amazing amount of text content about various pop culture things. Longest page on Wikia is the Luke Skywalker article on Wikipedia, which, if you print it, is 74 pages long. So that's what I spent the last couple of years making faster. So we wanted to make it faster, and it was pretty obvious that it was speed of light that was the problem. So a friend of mine just asked, a vendor just claimed that they can get us a 25K packet from London, from LA to London in 50 milliseconds. Is this true? No. That is actually, I mean, I guess you happen to come from the future and have neutrinos. I don't know. Like, it is impossible, right? So based on the speed of light, in a perfect fiber link, it would take 180 milliseconds. And we don't have perfect fiber links because they don't go over Greenland to San Francisco. So 50 is pretty ridiculous, unless they actually meant from the time that they start sending the 18 packets needed with no windowing until they get to the other side, which you can do in 50 since it's one way out of the handshake. So you skip the handshake, you skip the request, you can do it. And we decided to build our own CDN. And we built our own CDN because we needed instant purging. And apparently that's something that all the other CDNs think is impossible to do. That I'm pushing configurations faster than 8 hours. So we built it, and we're like, we didn't know. How hard can it be? What do? You need a colo, you need servers, you need global load balancing, and then you go. So I went. I flew to London with 2 servers, and went like, I'll fucking try this. The TSA liked it. This is the most upper-class traveled server in the world, probably. It was a very frightening moment when I was like waiting for the luggage, and the oversized luggage bin is like 2-3 minutes walk that way, and the normal one is 2-3 minutes that way, and I was like, which one do I stand by? Like, I have like $15,000 of hardware coming out of one of these belts. Like, which one do I stand by? Right? Man, no one took them. No one asked. I think people didn't actually assume there were servers in there. Like, no one would be insane enough to fly with servers, so they just thought it was something else. I did have to be present when the TSA searched them. So turns out you need a bit more. You need this DNS resolution, geolocation, you get the HTTP request, and then you get the origin request, then you wait for a response, then you send the response. So what does Arthur do? Arthur looks at all the alternatives and decides that there's actually no DNS server out there that works for what he needs. This happens quite a lot. My team knows to say no most of the time, even if they fail most of the time to say no. Don't write your own DNS server. I broke the Google bot. Wiki went offline. It was fun. Turns out that while it's legal to return A records before C names, some crawlers don't like that. So that was a fun period of time. The reason why we wrote our own is because no one, you guys hadn't really started yet, so don't give me shit yet, was that everyone else had static assignments based off state. And I looked at that and went like, fuck, I don't want that. I want like closest node. I don't want like statically assign all my locations to various locations. That works for countries, but it doesn't really work for the US. And so I just wrote my own. It was like 200 lines of Perl code, used like lib unbound, and took the long lat and sent you to the closest data center. It was really trivial. I probably violated like 19 patents while doing so, though. I actually just, in the DNS space, I actually just learned something over last week, which is I've always run a low negative TTL because I figured it doesn't hurt, and it means that if I add something new, it will appear pretty quickly. Turns out it doesn't actually hurt you. If you run a website and you don't have IPv6 and you have a low negative TTL, you force all your clients that know about IPv6 to reissue quad A requests every time that negative TTL expires. So we run a 30-second TTL and a 60-second negative TTL, which means that every 2 lookups, the client had to do 2 lookups for the quad A that we do not yet give out. So I was looking at DNS resolution traffic and or charts, and I was like wondering why this weird effect was happening. And then it struck me that this might be it. And I talked to Dyn, and they confirmed that that would probably be the case. And we changed it, and now those graphs look better. So, like, that's an illustration of like where things can be slow on like weird basis, even though you've been looking at something for a very long time. And so it's worth like re-examining, worth looking at something, and worth going like, why? If you see something weird on a chart, like go, whatever, like go look at it. Go like actually dig deep and find like what actually caused it. Now you won't be able to, you don't have time to do all of them because, it's shit all the way down. But take the ones that like look that they're important and go after them, and you'll usually, with enough persistence, and enough swearing, find out what actually is going on. One of the problems we've had a lot with finding out what's going on is monitoring. How many of you are developers in here? And how many of you are sysadmins? Great. So I'll start off by saying most developers don't know how to operate shit. And now I've insulted the developers. So now I'll go on to insult the ops people. And my background is very much both. I tend to float between, I'm neither, and I float between development and operations. A lot of the state of the shit we use is because it was written by ops people that don't know how to write code. Hello, Nagios. Thank you. Hello, RRD. Hello, like, on many fucking levels. And the problem is that these systems are good enough that no one actually goes around to re-implementing them, but they are shit. Hello, OpenStack. I'm sorry, you base a file system on rsync in like not the 1900s? Like, what's wrong with you? And monitoring has that problem, is that like a lot of the tools are pretty fucking bad. The other problem we have is that active probes are useless. Like, yeah, they're good for, detecting that things are down and stuff. They don't actually measure anything. Like, we have 25,000 requests per second at peak or something like that. If I do, I don't know, a request per second from 100 probes, that's still not a significant amount, and it's only measuring from those probes. And it turns out that most probe servers are located in pretty good network locations, because that's where it's cheap to get bandwidth. Or they're located on EC2, in which case you're not actually measuring your website, you're measuring how shit EC2 is. Or your favorite virtual service provider. So the best way to monitor is passive observers, and that's actually pretty hard at scale. We also monitor from each box to each box, but the passive observers is what we're trying to do the most of. So I'm going to disagree with you, Tom, here, based on your lightning talk. Every time I hear FPGA and ASIC, I go like, fuck you, Moore's Law is going to win. I once worked at a company that was unfortunate to buy an NFS server that was implemented in ASIC. That was really sad. A lot of people are turning off, a lot of the research now says that SSL accelerators are not worth it because Xeons are faster. TCP offloading, it's questionable if the network cards are actually supposed to do it or if the Xeon is supposed to do it, because guess what? The Xeon is faster. The CPUs have come a long way, and they get faster and cheaper, faster than the ASIC and the FPGAs go. So if you place your bet on them, over the long run, you will win. Over the short run, you will probably endure pain. It will also be cheaper, and you won't have to deal with a Cisco sales rep, which is always a plus. So we have simplified our deployment a lot. We don't have any routers or switches. Unless you realize that Linux is a very capable router, and we run Quagga on them, and we run BGP on them, and if you do IPR on one of our machines, you have 367,000 routes. Each machine has the full routing table. You'd think that this is slow. I've not been able to measure a performance impact of doing the routing on the machine itself at more than even doing about over a gigabit per second per port. And that's live traffic, and simulated traffic even way higher than that. I have not been able to detect that actually choosing which interface to go through the fib significantly slows it down. And I emailed you a paper that confirms that the maximum packet rate of Ethernet is 1.44 million packets a second. 1448. The question is what happens at 14 million packets per second, which is what 10 gigi. And then, of course, we have in the horizon 40 and 100 gigi, which is going to be its own fun. At 14 million packets, the highest end network cards can keep about 500,000 packets in their ring buffer at any given time onto DMA. So you need to pull pretty fucking quickly to keep up with them. Thankfully, our traffic is mostly outbound, not inbound. The good thing about this is that from a network point of view, there's no question that when a packet leaves us, the packet leaves us, right? Like ITCP dump, having Linux for your router is fantastic because you can TCP dump what's going on it. You no longer have to take an axe to it and open it up and see what's happening inside, or port mirror. But I know that when a packet is actually transmitted from my server, it is going to my ISP. There's no router, there's no ASIC, there's no control plane, there's nothing in between, sitting, probably written by a hardware engineer. So the people that are worse at developing software than most ops people are hardware engineers, which is why Cisco and all of that shit, and especially if you ever wonder why your printer sucks, it's because Canon and Sony only employ hardware engineers. And they also view themselves as hardware companies. So hardware engineers are even worse. And when they need to write code that's supposed to go into an ASIC, I don't trust them at all. Right? That shit is just broken. by design, I would say. So this way, we can maintain, like, we can time in packet to out packet and actually know when it's leaving our network. It's still problematic to monitor, like, network performance across the internet. There really isn't a good way, except, well, I'm hoping Boundary will eventually be able to provide me data. But the only way, really, is to, like, sample streams and look at them and install end-user JavaScript that measures performance. Sadly, the web timing spec is not yet fully implemented, and the navigation, the asset timing spec, whatever it's called, is not even implemented anywhere. But that is the only way to actually find out how fast you are, like, is to measure from the actual end users. And the network monitoring tools, probes, are useful, but don't rely on them for, like, finding out where. So as far as I can tell, no, I'm not going into that. One of the CDNs runs a 1-hour TTL and therefore appears to be faster than everyone else if you look at a network monitoring tool, because everyone else pays a penalty of a DNS lookup every 30 to 60 seconds. If you have a TTL of an hour and you go down, it's kind of hard to reroute. But you look faster on a monitor. So so what we look at is that it's like expected requests per second, cache hits, origin requests. We display those on charts. We alert on them. And we always look in the percentiles. Like, average is really freaking useless. It doesn't mean much or anything at all. And keeping track of percentiles for a long period of time is trickier, but it's than running a moving average. But it is significantly more useful. So this is our current generation hardware. It's pretty sweet. That should be 12x. I really wanted to get the 6-port 10 gig cards, but I can't really justify that. But those are really sweet. You can push 120 gigabits out of one PCI Express card. Remember that next time you're using a slow VM somewhere and going like, why is this slow? And it's slow because all the software stack above that hardware is shit. So we've gone through a lot of hardware iterations as well. And yeah, RAID cards, there's one you can buy these days if you're using drives instead of spinning Rust. And that's the LSI 9265 or 9285s. Turn off the write cache, turn off the read cache, throw away the battery, and just use them. And we did some benchmarks on that. It's pretty interesting. You go like, why is it slower with the RAID cache? And you go, well, so I have a 48 gig page or 85 gig page cache, and I have a 1 gig RAID card cache. Whenever I get a miss on that page cache, how likely is it that it's going to be in that 1 gig cache? Well, pretty fucking unlikely. So you're basically paying a RAM penalty and like a CPU penalty for looking up that cache on every single request, when you're basically never, ever going to have a benefit of it. And for the write cache, the SSDs are just faster with their supercaps than the disk is, than the card is. But every single network card we have kernel panics. Every couple of months in netif or interface receive. And we've tried pretty much every single vendor except Mellanox, which we're about to try. But the Intels seem the best, but they all fucking suck. The Intels are really cool because you can program them, and you can like direct based on TCP which RQ they should raise. So you can, if you ever virtualize, you can tie a VM to a set of CPUs, and then you can tell the Ethernet card to only send RQs for that IP to the CPUs that that VM runs, which is pretty cool. And you can get pretty nice performance improvements by doing that. But they still crash. We do have a hardware process where the biggest important thing is that we have a very good relationship with Supermicro. It's so fantastic that I basically have never purchased anything except over Google Talk. And that's the kind of relationship I want with a vendor. like IAM and go like, hey, can you sell me this? And he goes, sure, this is the price. And I go like, all right, that's good. And he goes, I need a purchase number. And I IAM him back a made-up number, and he ships me the stuff. We maintain a pretty good knowledge of the individual components. And we do some theoretical modeling, which is basically me and Jason like going out for dinner and going, is this going to work or not? And then use a napkin to discover that it's probably not, and then try it anyway. And we've tried a various set of different configurations. The only way we can actually test them is by putting them in production. We've never been able to fully test in synthetic environments. One day I hope I'll be there, but right now it's production. The good thing is that we can do things well, we have an unfair advantage. Data loss is okay for us, data corruption is not. But since data loss is okay, we are cache. We have a bit more ability to try, as long as we, our checksumming is good and everything, we're a bit more ability to try cutting edge stuff in our network. And we can also retry any gets that one server crashes, or we can send copies of our traffic to one of our new servers and see how they go. But it's actually really nice to be able to wipe a hard drive without being afraid. So, any questions? So Paul Henning asked me that a bit earlier, and I said I use FreeBSD 2.2 up to through 4.6 or 4.7 or whatever it was. And then I tried 5.0, and I never went back. I don't know. I've been told that the VM is better. The hardware support is less clear. Every couple of months, I go, fuck, I'm going to try another operating system, and that's when my team says no. And I think we'll maybe get there, but I'm afraid that they're just going to suck in a different way, and we kind of know how Linux sucks, and we know how to get around it. While if we switch to a new operating system, we'll have to learn a whole new set of suck that we don't know how to get around. So I wish someone would I wish someone would start a company, take Linux, and actually make a server distro for people like us. But I guess people like us don't pay that much. But like I don't want to talk to Red Hat. Like I would rather pay a kernel hacker to be a pet kernel hacker standing by than to pay Red Hat. And because I don't actually believe Red Hat cares about what I do, right? They care about large enterprise installations. Yeah. Is there a question from back there? Okay. Oh, more questions? One more question, okay? No. We use a bunch of external services. We use Herconas, we use Pingdom, we use BrowserMob, we use Catchpoint. By using a lot of them, we kind of get like, oh yeah, no, Miami isn't actually bad. It's just this monitor station, this vendor's monitor station in Miami that's bad. So yeah, we use a bunch of them. And I mean, they provide use, but they don't actually tell us how fast we are. Right? They don't tell us how we perform for everyone. They just tell us we're up or down, and roughly, what they're useful is like direction, right? Like if they're you can see if you're slowing down or if you're speeding up, but you can't trust the absolute values coming out of them. Yeah. I will, actually, I would do this. I would feed it into Google Analytics. which is what Wikia does. I actually had the keynote open this when I opened it I opened keynote earlier. So what you see here is the page distribution of, actually this one, of the page speed loaded of Wikia. So they basically create a fake URL and record it in GA. And that means you get it per browser, per region, per location. That's why I know that the Comcast users in Northern California sometimes get a DNS server in Utah, thanks to Google Analytics. So, but otherwise, I don't know how I'd scale it. I would have to figure it out. But that said, GA, if you can figure out how to fit data into GA, it's a fantastic data warehouse tool. And it's kind of free. Any other questions? OK, thank you.